So what's really preventing the scalability of ADAS and AEV right now? And it really comes down to the fact that most and all AV stacks rely on millions and billions of miles of training data in order to understand what the world looks like around them and how the world is changing. Now, this really has some, I would say, gotchas that you find later on in your development program. You can do a few demos, and that's great. But this means every new geo that you go to, every new city that you launch in, you're out there collecting another million miles of data. You're remapping the whole area. You need to build up an HD map. Every new vehicle model that you go to, same thing. Every new sensor that you want to use, maybe you have a cheaper one, better one, higher reliability, you're training again. So this really presents an ongoing and high development cost for your deployed AV solutions. So what we have done here at BlueSpace is provide a perception solution that requires no training data, no HD map, which means that you build it once, and you can use the same software and hardware anywhere you go and across many different models and different locations where you might want to put this. We also get to performance that wasn't really feasible before with 3D LiDAR that lets you make L3 plus level decisions. And I want to start here with improved reliability. In the case in which I mean reliability in the detection of objects and how they're moving so we can make decisions. Now, existing AV systems really struggle from the long tail. Everybody's heard about the long tail. But I'm here to tell you that the long tail isn't just about getting more and more data to cover every possible scenario. It's really a combinatorics problem. It's not just, you've seen pedestrians before, you've seen bicyclists before, but as the Uber incident that other speakers mentioned later, it's really the combination of these different things coming together that you're never going to achieve with just collecting data. You're not going to catch every possible combo of objects and colors and lighting and so on that'll cover everything. So we can't just train our way out of this. And with our generic approach to object detection, which is a motion-first approach, we have a generic way to represent all objects to provide the information necessary to make motion decisions and safety decisions. This also comes with the benefit of faster reaction time. Since, as Ralph mentioned, you get your Doppler shift with every pixel, we can take that and actually get the full motion state of the object, which includes their linear and rotational velocities, and do that in a single frame of information. So instead of waiting, if your sensor's at 10 hertz, instead of waiting for 1, 2, 3, 4 frames of data before you make a decision, that's 300 milliseconds gone, just waiting for data to come in. We can give you that information in a single frame to react immediately to sudden events. We also have the benefit of having overall reduced compute. This can work on existing automotive qualified processors. We don't need a special AI chip or GPU hardware that's going to draw down your power and reduce your electric vehicle's overall range. So here we'll have a bicyclist just suddenly cut out onto the road, and instantaneously, the first time it's in the sensor's field of view, we have its motion and where it's going. And as the bicyclist is zigzagging across the street, reception software is able to detect not only that they're there, but they have this zigzag motion. This is another bicyclist example here in San Jose, where this bicyclist will cut right into the road and cut across all the lanes just because they felt like it. But these are the types of situations that we need that 2-second advantage to be able to detect their motion instantly, so our downstream control functions can have the time to react and make safe decisions to keep vulnerable road users and pedestrians safe as well.